So even if it was a cos omega t plus phi, that represented simple harmonic motion of amplitude a, right? Now suppose we had the following. X is a sine omega t plus b cos omega t. We had a sine omega t plus b cos omega t. Now this could have been written as root a square plus b squared into a by root a square plus b squared sine omega t plus b by root a square plus b squared cos omega t, right? Now suppose you chose to call this as cos phi and you chose to call this as sin phi, right? So this would be sin a cos b plus sin b cos a, sin a cos b plus sin b cos a, sin a plus b, right? So this is like root a square plus b squared sin omega t plus phi. Hey, this is simple harmonic with amplitude being root a square plus b squared. Therefore, a motion of this kind is also simple harmonic with amplitude being root a square plus b squared being the amplitude of motion. Yes or no? Right? Suppose now, can I wipe this off? And in fact, you could have checked it by differentiating as well. Let's do that. X dot is a omega cos omega t plus b minus b omega sin omega t, right? X double dot is minus a omega squared sin omega t plus minus b omega squared cos omega t. Now if you took minus omega squared common from this, then you get this as a sin omega t plus b cos omega t is what appears here, right? Hey, but a sin omega t plus b cos omega t is x. So then this turns out to be minus omega squared x. This turns out to be minus omega squared x. Therefore the motion is simple harmonic, right? Suppose, sounds all right, right? Can I wipe this off? Suppose we had x is a plus b sin omega t. A plus b sin omega t. Suppose that's how x was, right? Okay. I want to see if this motion is simple harmonic. I want to see if this motion is simple harmonic. So I differentiate once. I get x dot as b omega cos omega t, right? I get x double dot as minus b omega squared sin omega t, right? Now this b sin omega t could be written as x minus a. This b sin omega t I write as x minus a. Now the way to read this is, the way you can read this is as follows. This is actually acceleration. This is acceleration. Left hand side is acceleration proportional to displacement not from x equal to 0 but from x equal to a. Yes or no? This is a point x naught equal to a, and the acceleration at any given x is proportional to how far it's from A. Yes or no? Therefore, this motion is also simple harmonic, except that the mean position is not x equal to 0 but is x equal to A. Displacement is proportional to how far it's from x equal to x minus A is the distance from A of the any given x. Yes or no? So, this motion is also simple harmonic with mean position not being x equal to 0 but being x equal to A. Right? The way things happen here is the maximum x can be A plus B, isn't it? The maximum value of x can be A plus B. The minimum value of x will be A minus B. Do you see that? Because maximum sign is plus 1, minimum sign is minus 1. So the motion is like this. X max is A plus B. X min is A minus B. And the mean position is x naught equal to A. This time the mean position is not x equal to 0 but is x equal to A. Right? And what's the amplitude of motion? No, B. B are distance between the mean position and the extreme position. That's the amplitude of motion. This is B units. The amplitude is B. The amplitude of this motion is B. Not A. The amplitude of this motion is B. Mean position is x naught equal to A. X max is A plus B, which is B units to the right, and it goes B units to the left of x equal to A. Right? Do you all get this right? Okay, now, so even if it was cos omega t, same thing. A plus B cos omega t would also be simple harmonic with amplitude equal to B. Amplitude equal to B. Right? Both sine and cosine constitute simple harmonic motion. Both sine and cosine constitute simple harmonic motion. Now, suppose I had x equal to A cos square omega t. I want to figure out what kind of a motion is this. X equal to A cos square omega t. Right? Now, cos square omega t means half of 1 plus cos 2 omega t. Yes or no? Cos square theta, half 1 plus cos 2 theta. Right? Which is like a by 2 plus A by 2 cos 2 omega t. Hey, a motion like this, so which is like A by 2 plus A by 2 cos some omega prime t, where omega prime is 2 omega, omega prime is some 2 omega, right? Again, what kind of a motion is this? Simple harmonic with amplitude equal to A by 2, amplitude equal to A by 2. So x equal to A cos square omega t is also simple harmonic, right? What about, however, it can go A by 2 plus A by 2 and A by 2 minus A by 2 maximum. So mean position is A by 2. Now, what about x equal to A sine square omega t? What kind of a motion is this? Simple harmonic, because this I could have written as A by 2 into 1 minus cos 2 omega t. So which is like A by 2 minus A by 2 cos 2 omega t. Yes or no? Which will also be simple harmonic. In fact, let me tell you, x is A sine omega t is simple harmonic. X is minus A sine omega t will also be simple harmonic. Yes, yes. Because see, if you differentiate this, you get what? X dot is minus A omega cos omega t. Differentiate one more time, you get x double dot is A omega squared sine omega t. Right? But A sine omega t is what? Minus x is minus x. So this is minus omega squared x, which is also simple harmonic. Similarly, x is A cos omega t is simple harmonic. X is minus A cos omega t will also be simple harmonic. right? X is a cos square omega t or x is a sin square omega t, both will be simple harmonic. Do you all understand this? Now, F equal to minus kx represented what? Simple harmonic motion with force constant k. And how do you obtain the equilibrium position? When you put F equal to 0, the corresponding value of x gives you the equilibrium position. So in this case, how did I get the equilibrium position or the mean position? Plug in F equal to 0, that gives me x equal to 0. This then would be the equilibrium position or the mean position. Isn't it? That's how you got the equilibrium position or the mean position. And then it went, say, a units to the right of this or a units to the left of the mean position, where a is the amplitude of motion. However, suppose a particle is being acted upon by a force of this kind, not minus kx, but minus kx plus some c. Suppose a particle is being acted upon by a force which is not minus kx, but minus kx plus c, and I want to figure out the nature of motion exhibited by this particle, right? Now, this could have been written as minus k into x minus c by k, and c by k I can refer to as some x naught. C by k I can refer to as some x naught. So this is like minus k into x minus x naught. Now, what kind of a characteristic is this? This is x equal to x naught, and this is some x. First of all, do you realize that at x equal to x naught the force is 0? So force at x naught is 0. Therefore, this is the equilibrium position. This is the x naught is the equilibrium position. Next, when the particle is moved at x, what is its displacement from x naught? X minus x naught is its displacement from x naught. The force acting on the particle is proportional to how far it is from x naught and oppositely directed. So what kind of a motion is this? Simple harmonic with equilibrium position not being x equal to 0 but being x equal to some x naught, which is c by k. However, the force constant for this is k, the force constant for this is also k. What has changed is only the mean position. Only the mean position has got altered. Yes or no? Yes, sir. Right. Now, so if someone said if a is minus omega squared x is simple harmonic, then a is minus omega squared x plus some constant will also be simple harmonic. Clear? Now, so far so good. Simple, right? Now, x is a sine omega t plus phi. Okay. X is a sine omega t plus phi. This is x at time t equal to t. Displacement of the particle at any given instant of time t. Clear? Now, do you realize it could have been written as a sine omega t plus 2 pi plus phi? The sign will remain the same if I add 2 pi to the angle, right? This is like x equal to a sine omega t plus 2 pi by omega plus phi, right? Yes or no? I took omega common from these two terms, t plus 2 pi by omega. Yes or no? Okay, this is displacement at an instant of time t. Do you realize this is displacement at an instant of time t plus 2 pi by omega, right? So that means one thing, the displacement of the particle at an instant of time t is the same as the displacement of the particle at an instant of time t plus 2 pi by omega. 1. Next, what's the velocity of the particle? Velocity of the particle at any given instant of time t can be obtained by differentiating this, which is like a omega cos omega t plus phi, right? Now, this could also have been written as a omega cos omega t plus 2 pi plus phi. Clear? This could have been written as a omega cos omega t plus 2 pi by omega plus phi. Yes or no? This is v at an instant of time t. This is v at an instant of time t plus 2 pi by omega. Yes or no? Yes, sir. Right. So this is v at an instant of time t plus 2 pi by omega. Now, the two conclusions. One, x at an instant of time t is the same as x at an instant of time t plus 2 pi by omega. Right? Similarly, velocity at an instant of time t is the same as velocity at an instant of time t plus 2 pi by omega, implying therefore that 2 pi by omega seconds after t, after a certain instant, if this is that certain instant t, then 2 pi by omega seconds later, the displacement gets replicated, the velocity also gets replicated. In a time equal to 2 pi by omega, both displacement and velocity get completely replicated, reproduced. Yes or no? Right? Now, can I wipe this off? Right. Almost all of you are getting it right. Now, see, for the oscillator, therefore, this was, let's say, the mean position. This was a point P. These were the two extreme positions, right? Now, what was referred to as a full cycle? The particle went from P to this position, turned around, came to this extremity, turned around, and came to this point P once again, right? This is what the particle did in a full cycle, right? Now, in a full cycle, see, the particle went to P, to the extreme position, and then came back to P. But then, when it came back to P right after that, its velocity didn't get replicated, because the direction of velocity was leftwards here, and when it started, the direction of velocity was rightwards. So when it did this, only the displacement got replicated, but not the velocity. Now, you didn't understand this. See, when it started at P initially, it was moving rightwards. It went to, say, S, and then it turned around and came to P. Then its displacement got replicated, but not its velocity. Why? Because when it started, its velocity was rightward. Now when it came to P, its velocity was leftwards. So this is not a full cycle. In a full cycle, not only is the displacement, but also the velocity must get replicated. In a full cycle, see, in a full cycle, what is happening? The particle comes back to P, but its displacement replicated, but not velocity. Now it goes back and turns around and comes back to P. Both its displacement and velocity now get replicated, because see, the particle is headed in the same state. The state of motion that it started with at P, it's in the same state of motion on arrival at P in a full cycle. So state of motion is not just about the speed of the particle, but is also about the direction of motion of the particle. When I talk of the state, the kinematic state of the particle, I'm talking about two things: the position of the particle, which is P. I'm also talking about its velocity, which includes, which packages both the magnitude as well as the direction. So in a full cycle is the smallest time in which both the velocity and displacement get replicated. A full cycle is the smallest time in which the displacement as well as the velocity get completely replicated. You know what I'm saying? So in this time, do you realize this is the shortest time? This full cycle is the shortest time in which both the displacement and velocity get completely reproduced. And do you realize that this time is 2 pi by omega? In a time equal to 2 pi by omega, both x and v get completely replicated. So this must represent the time period of motion, which is 2 pi by omega. Must represent the time period of motion, which is 2 pi by omega. Right? Now, the frequency of the particle would be 1 by t. Right? So this 1 by t, if I write as n, then omega turns out to be 2 pi n. Omega turns out to be then 2 pi by n. See, omega is 2 pi by t, where 1 by t is n. So this is 2 pi n. This is 2 pi n. And 2 pi is in radians, n is in per second. So this is radians per second. This is radians per second, and is called the angular frequency. And is called the angular frequency. For the oscillator. This is called the angular frequency for the oscillator. Right? Got it? Now let me throw some light on that constant of integration phi that emerged, and let me tell you how useless it is. Okay. The displacement of the particle as a function of time was a sine omega t plus phi. Okay. And a particle was executing simple harmonic motion in a lab. There was this weird scientist carrying out this experiment in the lab. Okay. The particle was moving about between R and S, the amplitude positions. Right? And he tells 3 of his students to examine this motion and report the phase constant for this particle. 3 of his very dumb students were asked to report phi, the phase constant of this motion. Okay. Now, the particle was executing SHM, all right, with amplitude A and with angular frequency omega. Now, one student starts to observe the particle when it was at the mean position and was moving to the right with a velocity v naught. Student 1. Right? And he was entrusted the responsibility to calculate the value of phi for this motion. Right? So he says, once he starts observing, so he would call the instant of time when he starts to observe as t equal to 0, isn't it? So from the point of view of the student, at t equal to 0, x was 0. The particle was at the mean position at t equal to 0. Right? So he says, all right, put x equal to 0 when t is 0. Put x equal to 0 when t is 0. Right? And then he gets sine phi equal to 0. Now he's confused. Phi could be 0 or pi, for example. He wants to figure out whether phi is 0 or pi. So then, not that dumb, he differentiates this to find the velocity of the particle, because he understands that the particle is moving to the right, so its velocity at this instant must be positive, right? So when he differentiates this, he gets a omega cos omega t plus phi. At t equal to 0, v was v naught and was positive. At t equal to 0, v was v naught and was positive. Right? So v naught is a omega cos phi. Right? Now phi must be such that v naught must turn positive. Therefore, can phi be pi? Because when phi is pi, cos phi is minus 1. So phi equal to pi is ruled out. Phi therefore must be 0. Phi therefore must be 0. Therefore, here he goes back to his professor and he says, the motion is described by x is a sine omega t. Phase constant is found out of a lot of hard work, 0. This is student 1. Okay. Student 2. Okay. Student T2. When this student goes there, he finds that the particle is at x equal to, say, a by 2. He finds that the particle is at x equal to a by 2 and is moving to the right at t equal to 0. Moving to the right, say, with a velocity some v1. So he says, all right, at t equal to 0, let me plug in x equal to a by 2. That leads to sine phi equal to half. Phi could have been 30 degrees or 150 degrees, right? Phi could have been 30 degrees or 150 degrees, right? So he has to figure out which of the two is appropriate, pi by 6 or 5 pi by 6. He says, all right, let me differentiate this one more time with respect to time. So v is a omega cos omega t plus phi. At t equal to 0, v was v1. At t equal to 0, v was v1. So v1 equal to, at t equal to 0, it turns out to be a omega cos phi. Yes or no? And since he was observing the particle to be moving to the right, v1 ought to have been positive. Now phi equal to 5 pi by 6 would have given me cos phi negative. Therefore, this must be ruled out, because this would make cos phi negative, but v1 is positive. Therefore, what's the appropriate value of phi? Pi by 6. So this student says, okay, phi is pi by 6. And the nature of motion is x is a sine omega t plus pi by 6. The third student he found the particle at x equal to a by 2 when he started to observe, and the particle was moving leftwards with a velocity v1. Right? Therefore, for him, again the same thing. At t equal to 0, x was a by 2. Phi could have been pi by 6 or 5 pi by 6. But v1 should have been negative. So cos phi must have been negative. So phi must have been 5 pi by 6. So for this, phi is 5 pi by 6. 3 students come down and report 3 values of phi. A 4th student will come and report a 4th value of phi. 100 students might report 100 values of phi. The same student coming at different times will report different values of phi, right? Which means this phi is a piece of it makes no physical sense. It's a observer's perspective. It's simply an observer's perspective. It's about when you start to observe this motion, the particle, there is nothing fundamental about this. The fundamentals about the motion are 2 things, the amplitude and omega, right? And these are 2 independent entities. They are unrelated. Omega and A are not talking to each other in any form, right? These are 2 fundamental things about the motion. Phi belongs to the observer. Different observers will report different values of phi. There is nothing fundamental about phi. There is nothing fixed about phi. So if you decide that this will be t equal to 0, then phi will be fixed. But if you have not decided what t equal to 0 will be for the motion, then phi can have any value based on who starts to observe and when. Right? Now, I will give more meaning to this omega down the line, but the simplest illustration that I can offer to you, physical, where the particle executes simple harmonic, is, let's say, a particle of mass m resting on a smooth surface, horizontal surface, attached to a spring of force constant k, spring constant k, right? And say this is the natural length of the spring, natural state of the spring, unstretched, right? And now, if someone pulls the spring by a small, by an amount, say x to the right, by an amount x to the right, if someone pulls the spring, then the spring will exert on this a force kx to the left. If you pull the spring to the right by an amount x, the spring will exert a force kx to the left. This was the point where there was no net force acting on m. Therefore, this could have been referred to as the equilibrium position. This could have been referred to as the equilibrium position, no net force acting. And the force, this should have been then referred to as a restoring force, because any attempt to displace it from the equilibrium position is met with resistance, right? This force kx opposes the motion x units to the right, will act leftwards, attempting to bring the particle to the mean position, right? Restoring force proportional to how far the particle is from the mean position. The motion therefore must be simple harmonic, right? And the force constant for this motion must be k. Therefore, the angular frequency of this motion would be root k by m. Omega squared is k by m, so omega would be root k by m. The time period of oscillation of this particle is going to be 2 pi by omega. That means 2 pi root m by k would be the time period of motion, right? Now, what about the amplitude? Hey, if you displace it by an amount 3 centimeters slowly, you displace it slowly by an amount 3 centimeters to the right, very slowly, that means, and release it from this point, right? The velocity of the particle is 0 at this instant, right? Therefore, this must represent an extreme state. If you are moving the particle very, very slowly to the right, that means you are not building velocity of the particle. The particle comes to the state displaced 3 centimeters from the equilibrium position with 0 velocity, and then you release the particle. The particle will be subject to restoring forces proportional to displacement from the mean position. Motion inevitably, for sure, would be simple harmonic, and at this point, since the velocity of the particle is 0, this must represent an extreme state. The point where the velocity of the particle is 0 must be an extreme state with respect to the mean position. Therefore, this must be the amplitude position. And therefore, the amplitude that you have built into the particle is 3 centimeters. Right? What would be the omega? If 3 centimeters is the amplitude, omega would be root k by m anyways. Right? Suppose you displace it by an amount 5 centimeters to the right and then release. Very slowly you move it right 5 centimeters to the right and release. Then this would be the new extreme state. This would be the new amplitude position. The new amplitude therefore would be 5 centimeters. Omega however will remain root k by m. Displace it 7 centimeters to the right, very slowly move it to the right and release. Amplitude would be 7 centimeters, omega will still be root k by m. Meaning therefore, even though omega and amplitude are fundamentals to the motion, you have handle over amplitude but you don't have handle over omega. For a given system of oscillators, or for an oscillating system, until and unless you get brutal with the spring, break it up into 5 different pieces, use one piece one way, another piece another way. If you're not that wild, you're just mild with it, let it be the way it is, then you can't change omega, you can't change the force constant of this motion. But nature will always allow you the amplitude that you want to build into the system. So amplitude belongs to us, omega belongs to the system. Got me? Is that okay? No, yes, time period will not change. Time period will be fundamental. Omega and k will be fundamental. Right? But amplitude would be dependent on us. Stand by.